We've got quite a bit to get through today because, as you all know, we missed a lecture on Good Friday, and I want to try and cover at least the basics of the lecture that we, well, I guess it's lecture 16 today. Obviously, the lecture notes are up on the web, up on Moodle, and I also uploaded a recording of lecture 16, which is the one we'll have to go through in a little bit of a rush at the end of today. But it's really important we do that so that we keep on track of when all your labs are going to be, because there's no point having your labs in advance of what we've covered in the lectures. The assignment is coming out very soon. I was hoping it was going to be out this afternoon. I'm just conferring with my colleague at Sunway. I'm guessing now that it might not be out until Monday. You'll have about 4 weeks to do that before it's due around about the end of semester. Obviously, I'll give you the exact details when it comes out. I can wait here all day for you guys to stop talking, and we can be here a lot longer. Come on, please be quiet. That's better. Okay. Recap. What have we done so far? We looked at root finding, we looked at bracketing methods, 2 different bracketing methods, and open methods, 3 different open methods. We saw that the bracketing methods, the key factor of the bracketing methods was that you had to have 1 point on either side of the root, so the function had to change sign. And if you could get that, then you're guaranteed to be able to find the root. Not necessarily efficiently, but you could do it. The open methods we saw were almost the same method. The only thing that was different about the open methods was really the way in which you estimated the derivative that you were using to find an estimate of the next value of the root. And I hope you've probably done a bit of that in the labs this week. You should also know what the pros and cons of the above methods are. So we know that these 2 are guaranteed to find a root, but they can converge slowly. We know that these ones, when they work robustly. They work rapidly, but they don't necessarily robust. They can diverge, they can get into infinite loops, they can go off to infinity, they can find something which is not the root that you're looking for. So you've always got to be aware, when you're doing something like this, that you actually understand what it is that you're doing. If possible, you try and plot the function to see what it looks like, to see where you think a guess for the root might be. You start off with a good guess for the root, you're more likely to converge to what you're after. If you start off with a random guess or some bad guess, you could diverge, you could find the root you're not looking for, a whole bunch of other things. We also saw that optimization can be framed as a root finding problem. So optimizing a function, which is usually meaning taking the minima or sometimes finding the maxima, effectively is like a root finding exercise on the derivative of that equation. Okay, so there's like many things in mathematics, you can frame things, quite disparate things in the same kind of way. So optimization and root finding are very, very closely related. Today, however, we're going to do something a little bit different. Let's just go back and have a look at our bungee jumper example. And let's imagine we're actually trying to take some measurements of the drag coefficient. And so what we've got here is we've got some kind of large diameter tube, we've got a fan at the top, we're pumping down a whole bunch of air, and our poor old bungee jumper's strapped in here inside this large tube, and we're pumping air down here at a velocity that we can measure. And he's actually attached to some kind of harness which is on a strain gauge here. Okay, so what we're trying to do is we're trying to measure, as a function of the velocity of the air that's impinging on the bungee jumper, what extra force, not talking about the gravity force, the body force now, we're talking about what kind of drag force are we going to get on this guy. Okay, so this is a kind of test rig, and we might do this, and we might get the following set of measurements at a range of different wind speeds from 10 to 80 metres a second, and we measure the force, the drag force, using these points here. What's the first thing you're going to do when you have some experimental data? I hope you know this without even thinking about it. You're going to plot it. You're going to see what it looks like. And if we plot that data, it looks like this. So it doesn't look terribly nice. It's kind of like jumping around all over the place. But this is what happens mostly in the real world if you're measuring something. Unless you're measuring something incredibly finely under unbelievably well-controlled environment, you're going to get a whole bunch of scatter in your data. And so for the case of the bungee jumper there, maybe the airspeed indicator wasn't working correctly. Maybe the bungee jumper was moving sideways a little bit in the tunnel, so that actually affected the measurement, the force on him, because the flow was lopsided. It wasn't even around the bungee jumper. So there's a whole lot of different reasons why this data might not look terribly nice. Okay, so the question is, if we wanted to try and fit some curve to that, how are we going to extract enough information there to understand what's going on? Now, in a previous lecture, we said that the force on something like a bungee jumper that's travelling at a reasonably fast speed is proportional to the square of the velocity. Let's just have a look at that. Does it look like the force is equal to the square of the velocity? That's certainly not really obvious. I mean, there's sort of low points down here, some high points up there, but the scatter is such that I actually don't know. If I looked at that, I'd be definitely very uncertain. Okay, so what today's lecture, the first part of today's lecture is all about, is trying to figure out how to fit a function to this, and then making some rational assessment of whether the function that we fitted to it is reasonable or not. And that's really important. You can fit a straight line to any data that you like. Okay, I can fit a straight line to that very easily using what we're going to talk about today. But the question is it sensible? Is it sensible to do that? And there's a whole range. There's mathematical measures of how good your fit is, but there's also physical, just basically physical arguments. Does it make sense if I fit a straight line to this data? And we'll see today that it doesn't necessarily do that. Before we go on any further, I'm sure that all of you know this, but I just need to make sure that we're all on the same page with a few really basic statistical comments, statistical measures. So, the first thing that's really important, I'm sure everyone knows, what the arithmetic mean of a set of numbers is. Okay, so if we have a set of data values, yi, we've got n of them, the mean value is the sum of those values divided by the number of values that we've got. Okay, and we usually indicate that by an overbar. So y bar is it's the mean value, usually often called the average value as well. We're going to be using the mean in what we talk about today. We actually don't need to know very much about the median and the mode, but you do need to know what they are in general. The median, if you take all of your data values and you rank them from smallest to biggest, the median value is the value that's right in the middle. So half the numbers are bigger and half the numbers are smaller. The mode is the value that occurs most frequently. And that can be anywhere in the distribution. It can be down the bottom end, it can be up the top end. And it bears no direct relationship to either the median or the mean. Today, it's going to be the mean that's the important thing that we're going to look at. Okay, so those are what's so-called first-order statistics. We also can look at what are called second-order statistics. So the one that you've probably all heard of is the standard deviation. So the standard deviation is given by this thing here. It's the square root of st divided by n minus 1, where n is the number of points. And st is the sum of the squares of what's known as the data residuals. And the data residual is how far away is my data point from the mean value. So if we take our data points, we subtract the mean value, and then we square it, and then sum all of those things up, we get this thing called st, and we take the square root of that divided by n minus 1, we have the standard deviation. This thing here is, this thing inside underneath the bracket here is often also called the variance. Okay, it's just equal to this thing divided by n minus 1, and if you just play around with the mathematics a little bit, you can actually see that it's equal to the sum of yi squared minus 1 on n divided by the average squared. You don't have to do all this stuff by hand in MATLAB like practically everything else. There are inbuilt functions. So if you have a vector that has a vector of numbers, you can actually just pass that into a function called mean, and it'll give you the mean. You can also pass it into median and mode. There are also functions that will give you the minimum and the maximum value of your data array, and something that returns the variance and the standard deviation. So just a really simple example. We've got a vector 1, 2, 3. We plug that into the mean function, the average value. Well, the average value of 1, 2 and 3, it's 6 divided by 3, it's 2. Doesn't matter whether this is a row or a column vector. Okay, you still get the same answer. However, if you pass in a matrix, in this case the first row is 1, 2, 3, the second row is 3, 1, 2, what the mean does is it averages down the columns. So you'll get a row vector coming out. Each element is the average of each of the columns. Okay, so 2 is the average of 1 and 3. 1.5 is the average of 2 and 1. 2.5 is the average of 2 and 3. Frankly, I can't see where you'd necessarily want to use that, but there might be occasions when you would. I think, certainly for this unit, I think you probably only need to use mean, variance and standard deviation. Okay, I've already said that. So we can use basic statistics if we want to fit a really crude approximation to our set of data points. We can take the average and say, well, okay, a really bad approximation to our function is that the force is equal to a constant, which is equal to the average value of what we've measured. Now, clearly, if we measure a different number of points, say we didn't take these 3 at the top here, we get a completely different mean. So we can see already that that's a really bad approximation to the function. Okay, so, but nevertheless, it's a model. It's an approximation to what we're trying to look at. A constant fitting a mean value is like fitting a 0th order polynomial. Well, let's fit a first order polynomial, a line, a straight line. So what we're going to do is linear regression, and basically a linear regression says let's try and fit a line that's in some sense best fits our data. So let's draw the line. It goes up here like this, and we're going to define the error of any particular at any particular data point as the difference in the function value at that data point minus what the straight line tells us. Okay, and so if we move this line, if we change the coefficients of that line and move it up or move it down, our errors are going to change as well. So what linear least squares regression says is we're trying to fit the line to those data points that we've got that minimises the error. So what we're going to do is going to calculate an error at each point. We're going to sum it up. Well, in actual fact, we're going to square it first, then sum it up so everything's positive. Then, on the basis of that sum, figure out what's the best straight line. It's the concept is pretty simple, and actually, it's actually not that hard to do. The mathematics is not even that hard. It's just a little bit intricate. So we can then define our errors as equal to y, which is the actual measured data point, minus the value that comes from our straight line. And what we're going to say is our straight line is going to be given by the equation a0 plus a1x. So the error will be y1 minus a0 minus a1x. We'll square that, we'll sum it up over all of our data points, and we'll call that thing SR. Okay, it turns out that the coefficients a0 and a1, you can find them, they're equal to this. a1 is equal to this expression here, so that's the sum of the x values times the y values, minus the sum of the x values times the sum of the y values, divided by, etc. That going on like that. Once you've found a1, you can easily find a0. a0 is just equal to the average value minus a1 times the average value of x. You are not going to have to remember those formulas, okay? They will be, in an exam question, they will be given to you if you need to use them. However, you do need to understand what each of the terms in that equation means. You do need to figure out how to calculate them and how to calculate the coefficients a0 and a1. Okay, so just going back to what we're actually trying to do with least squares, I gave you how to find a0 and a1. It's just a couple of simple formulas, but where do they come from? How do we actually figure out what they are? Well, we want to minimise, that should be SR, sorry, we need to do that by minimising SR. SR, remember we're given, I should go back to what it actually equals, SR is equal to the y values minus this thing squared, summed up over all the data values. We know what y, I and xi are, those are the data points we're given. We know what they are. The things that we don't know are a0 and a1. So you can think of this function here as being a function of our unknown coefficients a0 and a1. Okay? Because we're given the y's and the x's. So what we do is we take the derivative of this function with respect to a0 and the derivative of the function with respect to a1. So we're doing a minimisation. Okay? We're taking a function, we're taking the derivative, and then we're setting it equal to 0. But we need both of them to be equal to 0 simultaneously. So what you end up with is two simultaneous equations for a0 and a1. If you then solve that simple 2 by 2 system, you end up with these two things down here. You can actually do this for any function that you want to fit at all. It doesn't have to just be a straight line. If you wanted to fit a quadratic, you could go through a similar process, except now you'd have a 3x3 system. You'd have A0, A1 and A2. You could fit sines and cosines and a whole bunch of other things as well, and that's where Fourier series and the like come in. We're not going to cover those, however. Okay, so we've solved our equation for A0 and A1. These are the data values, x, y, for all of the different points. We need to calculate xi squared. We need to calculate xi times yi, so that's just 10 times 25 is 250, 20 times 70 is 1400, etc. Then we have to sum up all the x's, all the y's, all the xi squareds, all the xi's times yi's, then plug them into this formula. And we find out that A1 is equal to 19.47, etc., and that A0 is equal to minus 234 point something or other. So this is the straight line that, in some sense, gives us the best fit the experimental data that we've measured. Having a look at that, how do you think that's a good fit or a bad fit? What do you reckon? Sorry?
Bad.
You reckon it's bad? Why do you reckon it's bad?
Obviously, when the velocity of the air equals 0, the force should equal 0, whereas this is saying that it'll be negative.
Yeah, exactly right. But that's not a math. You're absolutely right. That's not a mathematical assessment of this. That's a rational, physical, logical assessment of this. If you look at this straight line, you're absolutely right. When the velocity is 0, the force should be 0, but it's not. So we can say that even though this sort of seems to go through a lot of the data points, physically it's meaningless once the velocity gets below about 10 or 12 metres a second. In fact, it's not only meaningless, it's giving us something that's completely unphysical. So a really important part of any of this kind of curve fitting is, once you've got your answer out, you've got to go back and have a look at what your answer is telling you. Don't just blindly go off and use it, because you design something to work at low flow speeds and your bungee jumper's in big trouble, right? Because you thought he had a negative force on him, but in actual fact he doesn't. So how can we actually measure the error in that linear regression? Okay, if we actually go back on that, apart from the fact that things are negative down there, let's just ignore that minor technicality. You look at this and you think, well, it fits pretty well for most of the data points. There's a bit of scatter up the top end here, but by and large, perhaps we could say that for greater than 20 metres a second, it's not doing too bad a job. But is it really? How do we actually quantify that? Okay, so we've, apart from the fact that we've got that negative thing, this regression result that we've just found, that if we say that this is an okay fit, it basically says that our upward force is proportional to the velocity, not to the velocity squared, which is what we had originally sort of assumed previously. Okay, but we need to check if it's an accurate fit or not, and there's a mathematical way of doing that. Okay, just doing things by eye is okay. Certainly, you need to do that first, because if you didn't do it by eye, you wouldn't pick up that the force was negative. But you also need to look at it mathematically. Okay, so the sum of the errors for the straight line is equal to this thing here, which is just the y value minus the value that comes out from our best fit, okay, squared and summed. I said before that the mean is just a simple model of the data. It's a really, really simple model of the data. One of the things that we're going to try and get at here is, how much better is our straight line fit? Is it really much better or not? So if we actually looked at the magnitude of the errors and plotted them on a normal distribution, we'd see that there'd be a lot of errors that were small, but then some errors that actually had quite large errors. What we expect too, that there's still going to be a normal distribution that describes the scatter of these errors, but we hope that it's going to be tighter because of our curve fit. Now, is that really true? Can we quantify that improvement? So what I'm going to introduce now is something called the coefficient of determination. Okay, it's called r squared, and what it's equal to is basically the variance minus our error on the straight line fit divided by the variance. So in other words, if this error here is 0, in other words, our straight line exactly fits the data, then our coefficient here is going to be equal to 1. It's just going to be st divided by st. And the curve, the fit is exact. If, on the other hand, SR is equal to ST, this thing is going to be 0. And what that's saying is, well, in actual fact, our fit with a straight line is absolutely no better than our fit by just using a mean. You know, the error in this is just the same as the error here. So we've actually achieved nothing. Okay, so I've already said that. In actual fact, R squared can actually be less than 0 as well, which means that just taking a mean value is actually better than trying to fit some kind of straight line. Okay, it's possible. It doesn't happen very often, but it's possible if that's the case. The key thing to remember is just because R squared is close to 1 doesn't mean that the fit is correct. Okay, sometimes you get a coefficient that might be 0.95, and you think, oh yeah, that's pretty good. But in actual fact, it's not necessarily that good at all. So this R squared here, in effect, in some sense, gives you a percentage improvement over fitting a mean value to the function by whatever method you've chosen. So if you're doing a linear fit, it tells you that 95% of the variation from the mean can be accounted for by our simple linear model. That's what R squared effectively is talking about. So just having a look at, if I can get this, I probably can't see enough of that. So this is actually something that's taken out of the textbook Chabra. Just going through here, we're passing in the x values and the y values. What we're going to pass back out is the coefficients A0 and A1, and we're going to pass out that coefficient determination, that R squared value. First thing we do is we come in, we see how long our vector x is, and the next little thing, which I'm sure maybe many of you wouldn't think of doing this, but we also check the length of y. Does x and y have the same, do x and y have the same length? In other words, are there the same number of x points and y points? If there aren't, then man, there is something wrong. We better not do anything on this data, we better throw an error message and get out. One of the things about good programming practice is you always trap things like this. You don't let them pass. Because if you wrote this and it actually, some crucial output was dependent on this and you inadvertently passed in some bad data and you got an answer out and you designed something on the basis of that, well, potentially you could be criminally negligent, but there's a whole bunch of other things that can happen as a consequence. So you need to do this kind of checking. So basically what Chabra does here, it converts to column vectors. I don't think you need to do that. Creates the sum of the x values, and you can do that. There's a function in MATLAB called sum. Creates the sum of the x values, the sum of the y values, the sum of the x squareds, the sum of the x times y's. He also does the sum of the y squareds. And then using those formula that we saw before, you just plug A1 and A2 in, and then we just calculate that coefficient of determination. And if we run that, of course can't see it because the window's not there, we get an error, not enough arguments. So that's a function, that's why. Okay. We'll come back to that, I think, in a bit. Okay. One thing about linear regression that you've got to be aware of is that, I said before, just because you have a good correlation coefficient doesn't mean your fit's good. Okay? Here are 4 sets of data that all are fitted linear in the linear least squares sense by the function 3 plus 1/2 x. Each of them has a coefficient of determination of 0.67, which says that 67% of the deviation from a constant can be explained by this straight line. Now you look at these data points, I mean, they're all completely different. You look at this thing here and you'd say, well, yeah, there's quite a bit of scatter in the data, but I can kind of believe that a straight line sort of approximates this. You look at this one down here and you say, yeah, not bad. I mean, there's this thing out here which seems to be deviating the line out. And in actual fact, it's things like this. If you saw this in experimental data, you'd want to go back and make sure that that point was a valid point, because there's no way it should be up there if this is really good data. But what this point does, it actually means that this would almost be a perfect straight line if it wasn't for that point there. So you need to go back and figure out what's going on at that point. Did something happen to the measurement there? Okay, because it doesn't look like it being correct. Now, just throwing it away because it doesn't look right is not the right thing to do. Okay, it might be a convenient thing to do, but you need to figure out why it's like that. Likewise, with these points here, it looks like the line should be x is equal to a constant. But wait a second, you've got this outlier out here as well. So again, whenever you see things that are obvious outliers, you need to try and investigate what the problem is. Likewise, for this one here, well, you can see that this seems to fit on a really nice function. It looks like maybe it's a quadratic, but trying to fit a straight line to it, I mean, you're clearly doing something wrong with this case here. But for all of these cases, the fit is identical in a linear least squared sense. Okay. Okay, so if we go back to our bungee jumper example where we've actually measured this data, we calculate the coefficients A0 and A1. We then calculate our coefficient of determination. It basically comes up to be 0.88, which means that approximately 88% of the original uncertainty away from the mean can be explained by fitting a straight line. So that's pretty good, 88%. You'd say, yeah, that's not bad. But as was pointed out before, you've got this negative force region down here. Something is definitely wrong with this model. We couldn't go away and use this model for design purposes. Okay, so, before we move on to the next bit, the other thing about linear regression is you can actually use linear regression to fit models that aren't actually y equals a0 plus a1x. So what does that actually mean? Well, there's three examples here which are quite common examples. Let's just quickly have a look at them. You can fit an exponential to your data. You can say y is equal to alpha 1 times e to the beta 1x. And the way in which you use linear regression to do this is you take the log of both sides of this equation, and so you end up with log y is equal to log alpha 1 plus beta 1 times x. And so you end up with a new set of variables, and your new variables are x and log y. So previously where you had y, you replace it with log y, and you fit a straight line to that. Then once you've got the coefficients alpha 1 and beta 1, you can go back and say what y is equal to. Similarly, with the power law, you can say, okay, I think that y is going to be equal to some coefficient alpha 2 times x to the beta 2 power. Likewise, as with the exponential, you take the log of both sides and you see that log y equals log alpha 2 plus beta 2 log x. Our new variables are going to be log x and log y, and we fit a straight line to that. Then we can convert back to x and y just by exponentiating them. And there's also a saturation growth rate model, which is, this is in lecture 16. If you look at the notes, we might get to it today. Y is equal to alpha 3 times x divided by beta 3 plus x. What you actually do for this case here is you actually invert both sides of the equation. So you've got 1 on y equals 1 on alpha 3 plus beta 3 on alpha 3 times 1 on x. And our new variables x and y are 1 on x and 1 on y. And you fit a straight line to those two things. And the coefficients we then find are 1 on alpha 3 and beta 3 on alpha 3, and then we can get back to the coefficients that we're actually looking for to fit into this model here. So this model here is not a bad model for the kinds of things you might see, for example, in some kind of fermentation reaction where you start off with a small amount of material, like your beer brewing. You put in a little bit of yeast, and eventually the cells multiply. That follows some kind of exponential growth rate, at least in the early stages. The saturation growth model in enzymatic kinetics, in chemical engineering, this kind of equation often fits a catalytic reaction rate. And this exponential here actually fits quite nicely something like a drag coefficient of a bungee jumper. So we're actually going to have a look at that in a minute. So what we're doing is when we're transforming these equations, in this case for the exponential from x to y, x to log y, this power law from log x to log y, and this inverse one here from 1 on x to 1 on y. But in these coordinates, when we do that transformation, these appear to be straight lines. So let's go quickly look back at our regression for the bungee jumper. We thought before that the force was going to be equal to the velocity squared. Well, let's not make that restrictive assumption. Let's assume that the force is proportional to the velocity to some power, and we'll call that power beta 2. So we're going to linearise this so we can do a linear regression by taking the log of both sides. So we end up with log f equals log alpha 2 plus beta 2 log velocity. And so our new variables are log f and log v, which take the place of y and x, and our unknown coefficients that we're trying to find are log alpha 2 and beta 2. They take the place of a0 and a1 previously in the standard linear regression. So if we put down our v and f, which is our x and y, as we did before, we take the log of x, put it in that column, the log of y, put it in that column, take the square of the log x's, the product of log x times log y, we sum them up, we put them into this equation, and we end up with our coefficient that comes out of here of a1 being 1.984 and a0 being negative 0.56. So our equation then is log y is equal to negative 0.56 plus that, but remember now we actually want to get back to x and y, not log x and log y. So we just exponentiate this, which becomes y equals alpha 2 x to the beta 2, or y equals force. Remember, force and y are the same. Force is equal to 0.2741 times the velocity to the power 1.942. Now 1.9842 looks pretty close to 2 to me. So the best fit for this data is actually a quadratic. The best power law fit to this data is almost a quadratic. So in the log f, log v coordinates, this is the straight line that we fit. When we convert that back to f and v, we end up with a curve, quadratic curve that looks like this. I don't think I'm going to go through this example in detail. It's in the lecture notes. I do want to make sure we cover off on the next lecture as well. But if you go through this, it's pretty clear what's going on. We've passed in v and we've passed in f that we've measured. We say, okay, I want my log x to be equal to the log of this and my log y to be equal to this. These are our two new variables. In actual fact, if I were going to do this, I'd just say x is equal to log v and y is equal to log f, and then just do a linear regression without complicating things. Okay, in fact, I'd probably even do this outside the routine and just use a standard linear regression. But this is the way it's been done here. We then do the sums that we need to put into the regression formula. When we just plug those numbers into A1 here and get A1 and A0, calculate the coefficient of determination. Now this is the coefficient of determination in that log x, log y space, not in the xy space. Okay, so this is the coefficient of determination in the straight line space. And then we invert things, so we see that we can go back to physical coordinates down the bottom, down there. Now what is... Okay, that's all right. Okay, so we fitted a straight line to begin with, and we saw that the correlation coefficient was 0.88. We had that problem down the bottom end where the force was negative. The correlation coefficient for this approximation here, so the coefficient of determination for this expression here, and what we've done now is we've gone back to physical units and done this as a function of the curve fit here and the actual data value we've got rather than the linear ones. We can see that r squared, or we can calculate r squared being 0.80, or maybe 0.81 if you round up. So in actual fact, the straight line has a better coefficient of determination. It's 0.88 as opposed to 0.81. But we saw, if we go back to the plot, we saw that down the bottom end here, it doesn't go negative. So that's got to be an advantage. Got to be an advantage over the previous one, which gave us some unphysical results. So even though this doesn't look like it's as good, it's actually going to be a much better function that's fit for purpose. If we actually want to do some measurements and we want to do some predictions, yeah, there might be some error in here, but there's not going to be some catastrophic failing. Okay, so both models explain some of the data uncertainty, but the choice we make here is based on the physics of what's going on. And you can never divorce yourself from that physics or the chemistry or whatever it is that's actually important to the example. Okay, I've already said all that kind of stuff. Now, there are also some built-in functions. Actually, this is explained better in the next lecture, so I'm going to take it into the next lecture. So before we quickly go through lecture 16, are there any questions on anything that I've gone through there? No, that's okay. come and see me in consultation if you have any problems. So let's move on to the next bit, the catch up for lecture 16. So we've seen that there are some situations where we can use linear regression to fit curves, even though the function is not linear. So the power law, the exponential, that inverse one. But it's not possible always to convert your function into some kind of linear relationship. That only happens in a few really special cases. And there's going to be a whole bunch of things out there where you can't possibly use any kind of linear regression, even if you do some kind of strange transformations. So what we're going to talk about next is, okay, can we try and fit a polynomial then to this data? Is it essential to fit a straight line? Can we actually make the assumption that we've got some kind of polynomial that looks like p1x to the n plus p2x to the n minus 1 plus ... plus pn plus 1, some constant at the end there. So what we're going to try and do now, and again, we're going to do this in a least squares sense. So we might have 100 data points, and we might try and fit a sixth order polynomial, say. We're not going to do that. You can actually go through that process just like we derived a linear regression and do the same kind of thing here. You end up with bigger and bigger systems, and that's not something that's a valuable use of your time. MATLAB has some built-in functions, polyfit and polyval. They're two functions that are designed specifically to fit polynomials to data. What have we got? Okay, so polyfit finds the coefficients of the polynomial that fits the data in a least squares sense. So if you've got a set of x and y values, and you've got n of them, you pass x, y, and n into polyfit, and it returns a vector of coefficients. Now, this, to me, is a little bit counterintuitive, but it's just the way that MATLAB does things. The first coefficient, p1, is the coefficient of the nth power. p2 is the coefficient of n minus 1, p3 is n minus 2, etc., all the way down to the end. So pn plus 1 is the constant coefficient, which is x to the 0 at the end. So the indices are reverse of the powers. It would be nicer if that index corresponded to the power in some way. So polyfit can... okay, sorry, I made a slight mistake in that. N is the order of the polynomial that you actually want to fit. Sorry, it's not the number of data points in x and y. N is the order of the polynomial you want to fit, a second order, a third order, a fourth order. So what we're doing here in choosing some nth order polynomial is we're not fitting something that goes like x to the n, we're fitting each one of those polynomial terms, x to the 0, x to the 1, x to the 2, etc., up to x to the n. So for example, polyfit xy1 fits a straight line because you've only got a first order term. Polyfit xy3 fits a cubic, p1 x cubed plus p2 x squared plus p3x plus p4, and polyfit xy0 fits a constant. So in actual fact, polyfit xy0 will calculate the mean for you if you wanted to do that for some strange reason. Okay, so once we've used polyfit to fit a polynomial, again in a least squares sense to a set of data, presumably we're going to want to do something with that. So for example, we might want to calculate the data values that our approximation has over a range. And the way we do that is to use a function called polyval. So once we've calculated p, which is our vector of coefficients, we can then use polyval. We pass in this vector of coefficients that we've calculated from polyfit, and we pass in the value where we want to actually calculate the polynomial. In this case, we want to calculate it at the point 3.5. So this process of taking your data, fitting a polynomial to it, and then using that polynomial to estimate what the data points are at other points is called interpolation. Okay, so we got some data, we fit a curve, we then use that to calculate the values at places where we don't have data points. Okay? Remembering that these are still only going to be approximate because our polynomial is only a good fit in terms of least squares fit. So I think I've got this one on MATLAB. Okay, so what we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 data points. And what we've done to begin with is we've called polyfit x, y, 0. And then we've used polyval to calculate the function of that polynomial at 50 equally spaced points, going from 1 up to 9. So our original data was the blue points. We calculated the coefficients using polyfit. We then used polyval to estimate the value of that polynomial at those red data points. And then we can look at these red points and see how they compare to the blue points. Is the mean a good approximation to the function? No, it's a terrible approximation. Okay? Well, what happens if we use polyfit xy1? Well, we're now getting something which, this is the linear regression. It's exactly equivalent to the linear regression. We can see that that's improved things enormously. The errors are much, much smaller. Polyfit xy2. We're now trying to fit a quadratic. In actual fact, the quadratic looks like it might be a bit worse. And we can go back and look at the coefficient of determination. We'd probably see that it was. Third order, yeah, not looking too bad. Fourth order, that's starting to look a lot better. Fifth order, better still. Sixth order, looks pretty spot on. Seventh, eighth, well, something funny is starting to happen. Eighth order polynomial, going through 9 points. Turns out that if you have n data points, you can guarantee to fit a polynomial of degree n minus 1 that passes exactly through all of the points. So this polynomial here actually passes through all of our data points. Okay, so it's an exact fit to our data, but it's not doing anything very good down here. And if we actually try and go to higher orders, we see that things go completely crazy. Okay, so it doesn't make sense to try and fit a 12th order polynomial to 9 data points because the problem isn't well posed. Now MATLAB does something, and you'll actually see, warning, polynomial is not unique. You can't actually see this because my window is not big enough. The degree of the polynomial is greater than or equal to the number of data points, and it doesn't make sense to do that. MATLAB will let you do it, but you've got to read these error messages and figure out, oh, wait a second, it's given me a warning, what does it mean? What do I need to do? Okay, so it doesn't make sense to fit polynomials of high order. Okay, so we've been through all those. Oops. Okay, so this is the same thing now with just a different set of data points. We've got 6 data points here, and we're fitting a 5th degree polynomial. It identically fits them. Okay. If we went back to that 8th order polynomial that fitted the 9th order points, we'd actually find that our r squared value was identically equal to 1 because the curve went through all the data points. But it's not necessarily a good fit. Let's have let's show you another example. This dashed line here represents some kind of function. And let's choose 5 points on that function. So we've got 5 data points, and then we use polyfit to fit a polynomial. And the polynomial that will be fitted will be this solid line here. The solid line passes through the same 5 points. But if you compare those 2 polynomials, compare the actual original one, the dashed line, to the one that polyfit fits, you can see that there's an enormous amount of difference. R squared for this solid line here would be 1. It'll be telling you, yeah, your polynomial is an exact fit. It goes through all the data points. It goes through all 5 of the data points that you gave it. If you discretize this thing with 100,000 points, well, it's not going to be so good any longer. Okay, but because we've only chosen 5 points, it goes through all those 5 points, but it doesn't go through the rest of the function. It goes out a long way. Likewise, if we discretize a few extra points and we try and fit a higher order polynomial, we can see we can get some of these really wild excursions away from the original line. That's because we're going from an original line to a finite set of points, and from that finite set of points back to some kind of polynomial. And in that process, going through that loop, we're actually losing information. And this fit, particularly when you have high order polynomials, gets worse and worse and worse. As a general rule, you should be fitting low order polynomials for curve fitting and interpolation. Now, it said cubic up here. You can sometimes go a bit higher than cubic and get away and get some quite nice results. We actually did that in the example we showed before. We could get up to about 6th order and still look pretty good. The problem is, of course, that low order polynomials don't necessarily fit as well, and we saw that in the example. And 2nd order wasn't really probably even as good as a 1st order polynomial. This problem is especially problematic if the underlying model is nothing like a polynomial, and there's an example a bit later on that's like that. If we get to it, I'll show you exactly what I mean. And in some cases, you might actually want to fit multiple curves to your data. So you choose sections of your data and you fit low order polynomials, then you move to another section of the data, fit a different polynomial, another section, etc. The other thing I need important bit of information to get across is the difference between interpolation and extrapolation. So interpolation is trying to estimate a data value within the bounds of your data. So if your data goes from 0 to 10, interpolation says, okay, I've taken my data points, I've fitted a curve to them, and I'm calculating a data value that's somewhere between 0 and 10. Extrapolation is, well, what happens if I want to go bigger than 10 or less than 0? Okay? Extrapolation is basically predicting the future based on the data so far. So if you look at the stock market and it seems to be going up and up and up, and you say, yeah, tomorrow it's going to be even higher, and then you have a crash, then your extrapolation from today's data to tomorrow's data has done you a real big disservice. So extrapolation as a general error, as a general thing to do, is risky. Sometimes you should do it, but it's a risky thing to do, and you should never extrapolate a long way away from where your data is. As an example, this is the US population data from 1920 to 1990. We're fitting a 7th order polynomial, and then we're extrapolating to the year 2000. And our polynomial that goes through all these data points really nicely predicts that the population of America should have halved between 1990 and 2000. So that's just a really simple example of where extrapolation is incredibly dangerous. If you based government policy on this, you would have been completely stuffed. Okay. We've got just a little bit of time to maybe go through this first example quickly. So I mentioned before that one of the models that we're looking at was a model that looked like y is equal to some constant divided by, kx divided by some constant plus x. Okay. This is an example of an equation called the Michaelis-Menten equation, which is commonly used to model enzymatic reactions, sometimes in living cells in chemical reactors. Here, V is our reaction rate. Vm is the maximum, actually it's not the maximum initial reaction rate, it should actually be the maximum possible reaction rate. In other words, it can never react faster than Vm. S is the concentration of a substrate, and Ks is some half saturation constant. You don't need to worry exactly what it is, it's just a constant. So there's actually another Michaelis-Menten equation. It's a 2nd order one where now these things are all replaced by the square, but the coefficients mean exactly the same things. The 1st order equation looks like this blue line. So this is reaction rate as a function of concentration. The black line is the 2nd order model, and they intersect at the value of Ks here, which is equal to the half maximum rate. So if we measure some data, the question is, which of these two models is going to fit our data best? So we're going to use polyfit to do this. Okay, so the saturation growth rate conversion, we can linearise this. We didn't have to, we could have actually fitted a polynomial. We are going to linearise this example. 1 on y is equal to 1 on a3 plus b3 on a3 times 1 on x. So our new variables we're going to linearise with are 1 on x and 1 on x and 1 on y. Linearising the 1st order model and the 2nd order model gives us equations that look like that. And we can fit linear least squares to both of these models here. I am going to rush through this a bit. And in the linear space, these are what the curve fits look like. I think we can eyeball things and say this one looks a little bit better than that one there. It's a little closer to the data. We can also then calculate the coefficients of variation, which I haven't actually done here. But if we go back into the real space, which is V versus S, we can see that the curve fits much more nicely for the second order model. The example I was going to give before about coefficients is also in here. It's fitting multiple curves to a rocket velocity. So this is the profile here. If we try and fit a single polynomial low order, single polynomial high order, there's problems. So look, sorry we had to rush through that, but that's the only way we can catch up. So back on schedule Tuesday next week.